So this is chapter 30. So we can start off by defining the current flowing through a wire. So it's electric current. So we'll say that current I is the flow of charge through a segment of a conductor in a given time. So we can say that this current flows through a certain surface of a conductor which is perpendicular to the flow of the current. Current is a scalar quantity and the unit of current is ampere. So we can say that since average current is given below as I average equals delta Q over delta T, where delta Q is the charge flow, let's say it's the total charge flow, and delta T is time. So in this case, we have 1 ampere. 1 ampere of current equals 1 coulomb over 1 second. So the ampere is a coulomb per second. So 1 ampere is 1 coulomb per second. So the instantaneous current I is given as I, which is equal to the limit of the average current, which is dq dt. So that will be instantaneous current. So how does this look in a microscopic model? So let's look at the microscopic model of current. So this is the microscopic model. So let's consider a segment of wire of length delta x. So we have a conducting wire below. So this length here is delta x. And the area of a surface for this wire is A. And we can have charge carriers in the wire moving around. And we shall say those charge carriers will move with a certain drift velocity. So they will move with a velocity v subscript v, which is the drift velocity. And so they would cover this interval delta x with a drift velocity delta t. So if you multiply the drift velocity by the time interval, that allows them to cover that interval delta x. Let n represent the number of charge carriers per unit volume. So that is the section that is shown. Then we can say the number of charge carriers in the segment shown is given by n times A delta x. So it's just a number times the volume. So the number of carriers in that segment shown is n times A delta x. And then we'll say that the total charge delta Q in the segment is given by delta Q equals n A delta x times Q, where Q is the charge on each carrier. So we can say that then the average current flowing through that segment is given by, this is G, given by I average equals delta Q over delta T. So we already know that the definition of average current is the Q dt. So if we just divide it by the Q, then we can say I average is equal to delta Q, which is n A delta x times Q divided by delta T, which becomes n A times Q times V D, where the V subscript D is just delta x over delta T. So the drift velocity V D is equal to delta x over delta T. V subscript D is drift velocity. So that will be the average current in the wire. So the conductor consists of charge carriers that are just in random motion going about in the wire. That is the average current in the wire. If you apply an electric field to the wire, or if you put a potential difference across the ends of the wire by connecting the wire to a battery, then the pump, which is the battery, forces the current to flow in one direction by applying an electric field along the length of the wire. So instead of having random average motions, then you're going to have an actual current moving in one direction. So we'll talk about that shortly. So I'll just mention that we can create a flow of current along the wire by applying a potential difference across the wire. Okay, so I'll continue with the next section, which is creating a current. So this is 30.2, creating a current. So I mentioned that we can create a current by applying a potential difference across the ends of the wire. So I'll put that here again, and I'll just use the word conductor. We'll apply a potential difference across the ends of the conductor. In this case, I'll call it a wire, by connecting it to a battery. So let's say we have a battery this way. This is the positive terminal and that's negative. So you connect the wire across the battery that way. Okay, so the current is going to flow. So current direction is the direction of flow of positive charges. And in reality, it's just a convention. So we can say that when the battery is connected to the wire, the current I flows. The direction of I is the direction of flow of positive charge. So this is a convention because we know that the positive charges themselves cannot flow. It's mostly negative charges that are flowing. So if the current direction is a flow of positive charge, then it means the negative charges flow in the opposite direction to the current. So that is our convention. And so let's look at it again. So we look at our conductor again. So I'll say that let's look at the conductor with the potential applied across it. So I'll take this conductor again, and if we apply potential across it, then this is positive V, negative V, so the electric field flows through the conductor in this direction. So this is E. So the current flows this way. So we can say that the potential difference, delta V, produces the electric field E, which points in the direction shown. So we can say that there is now a net flow of current in the direction of E. So we can analyze this to see why the current flows. So that would be our model of conduction. We can analyze the motion of the charge in the electric field in order to model conduction. So we can say that, recall that when a charge is in an E field, it experiences a force F. So that force is given by Coulomb's law. So the force F is equal to the charge times the electric field, uppercase E. And this force is equal to the mass times acceleration of the charge. So we can say that suppose the E field is along the x-axis, then we can say that the force along the x-axis is equal to E times uppercase EX, which is equal to M times A subscript x. So that the acceleration A subscript x is equal to lowercase e, which is a charge, times the electric field along x over the mass M. So by applying the potential, we have created a force on the charged particles in the electric field, which gives them an acceleration A subscript x. And so instead of the charge carriers in random motion, once you apply an electric field this way, by applying a potential across the ends, then you force them to move in one direction. So let me put the charges in there. So now, instead of random thermal motion, they're going to be moving in one direction that way, which is the same direction as the direction of the electric field. So the electric field goes this way. So they are now in motion in one direction. So there's going to be a net motion or net displacement. So the net displacement is this way. So here net displacement is 0, and on the right the net displacement is to the right. So we can use kinematics to find drift velocity v subscript d. So let's say recall that v final x is equal to v initial x plus a subscript x delta t. This is one of our kinematic equations. And so if we want to find drift velocity, the drift velocity v subscript d is an average velocity. So we shall say this is average x velocity initially plus acceleration x times delta t, which is our average time for motion, where we know that ax is equal to lowercase e uppercase ex over m. So we can say drift velocity is given by v naught x average plus e uppercase ex over m delta t. But we can say that since initially we had a random thermal motion, when we apply the electric field, then the average time is called the average time between collisions, or mean time between collisions of the charges as they go through the material. So remember, there are positive charges in the material which are arranged in a periodic structure, and then you have random electrons which are bouncing about in there. And without the potential applied, they just bounce around everywhere, and their mean velocity is zero, their average time is zero. Once you apply potential, it creates an electric field one way, which forces them to have a net displacement in one direction. Okay, so we can say that delta T average is the mean collision time between electrons, and also between the electrons and the positive charges in the crystal structure. So that's a mean collision time, delta tau. So it's called tau, mean collision time tau. That's the Greek letter.
TAU.
TAU, yes. And then V naught x is equal to 0 initially. So before the electric field is applied, V naught x is equal to 0. So we can say that the drift velocity is just equal to E uppercase Ex over m times tau. We can now plug this into the formula for average current to get the following. So we take the formula for average current. So we say I average was equal to, what was I average? It was the number, the charge, the drift velocity times the area. So we're now going to replace V subscript with the term that we have up there. So we can say that I average is going to be N Q times A, and then the drift velocity is E subscript X over N times tau. Okay, so this gives us our current flowing through the wire or through the conductor. Okay, let's continue. So we're going to look at current and current density next. So this is 30.3. So we already looked at instantaneous current. We've already defined average current, and we can say that the current is, we said the current was a charge per unit time. So we can define current density, J, in a conductor or wire as a current per unit area perpendicular to the flow of currents. So we can say J is equal to current density, and it's equal to current divided by area perpendicular. So I use area perpendicular to the flow that way. So this again goes back to the diagram I drew earlier of the segment of wire with current flow through it and a segment of area like that. So this is what we are talking about. So we have this segment of wire. The length here is delta x, and this area is A. Okay, so we're talking of current density is a current per unit area perpendicular to the flow. So using our definition of current density is I over A, so it's going to be N Q, and then we have E X over M times tau. Okay, and let's see, E X over M, this is a drift velocity, where E uppercase Ex over M times tau is equal to the drift velocity. So you can say current density is N Q times drift velocity. So the same amount of current that flows through one segment of the wire or conductor is the same current that ends up at another segment. So if I take the conductor, this way, and I put this segment here, I put a certain barrier there, the amount of current flowing through this end is equal to the current on the other side. And the current density is the number density per unit volume times the charge times the drift velocity. So this is the area. The drift velocity is v subscript d for charge carriers moving one way, which is the flow of positive charge. So what this means is that the same amount of current flows from one segment of the conductor to the other, which means that the current cannot be current is conserved. So we say, since, let's call this point P, since the current flowing to a point P in the conductor is equal to the current leaving the point, we say that current is conserved. Okay, so by conservation of current, it means that current cannot be created or destroyed. Okay, so the current is conserved. So the rate of which current leaves one segment is equal to the rate at which it appears at another segment. So we can state the law of conservation of current as follows. So the current is the same at all points. Current is the same at all points in the conductor. So we can illustrate this the following way. The law may be illustrated as follows. Let's consider a branch of conducting material with a current flowing through it. So what we have is, let's say we have a branch like that. So we have a current I1 entering here. This is I2. And they combine and come out of this place, this end. This is I3. And this is I4. The conservation of current just means that the total current in one coming at one end is equal to the current leaving the other end. So the current entering the left branch is equal to the current leaving the right branch. So we have I1 plus I2 equals I3 plus I4. And this, of course, applies to all any number of branches. So this is current in equals current out. So we can say that the sum of all currents coming into one branch is equal to the sum of all currents leaving on the other end. Okay, assuming that we have multiple branches. So let's go on to the next section, which is conductivity and resistivity. So already we've seen several things about current. We've defined average current, instantaneous current. We've talked about the current density through a segment of the wire. And we've also seen a conservation principle for current, which means that the current flowing through one end of a conductor is equal to the current leaving the other end. And if you have multiple branches feeding current into a conductor, the sum of all currents coming in is equal to the sum of currents leaving. Okay, so now we can put this all together and look at some intrinsic property of the material, which is the conductivity or the resistivity of the material. So we'll say that, recall that we saw earlier that the current density, J, is given by what? N Q times drift velocity, a number density charge times drift velocity, where the drift velocity is given by the charge E subscript x over m times mean free time t. So if we put this into the into the charge density, then we have N Q, we have E subscript x over m times tau. Then we can put this together as N Q E tau over m times E subscript x, because all of this are constant. So the constant term in parentheses is called conductivity of the conductor. And conductivity, we shall use sigma for that. So let me put that there. It's called a conductivity, which is sigma of the conductor. So we can say that the current density J is equal to conductivity times electric field, where E subscript x is the electric field in the conductor. And all of this assumes, of course, that the conductor is uniform, so that the conductivity is a linear property. Yes, we're talking of a linear conductivity. So this tells us that the current density and the electric field are established in a conductor whenever a potential difference is present. And so we are saying that the current density is proportional to the electric field, where the constant there is the conductivity of the material. Conductivity, sigma, is intrinsic to the material, so it doesn't depend upon the presence of an electric field or current density. It's intrinsic to the material. So if your material is copper, it has its own conductivity. If it's silver, gold, whatever it is, it will have its own conductivity, which is independent of the presence of electric field or current density. We can say conductivity is equal to R over N. So this is the conductivity of the material. And then we shall say that the inverse of conductivity is the resistivity. So we can say that rho is equal to 1 over sigma. So inverse of conductivity is resistivity. So resistivity also is an intrinsic property of the material. So this is rho. It looks like a P, but it's meant to be rho. This is the Greek letter rho. So we shall learn about the symbol omega. Okay, so that symbol is called omega. So we'll learn about that next.